Okay, I think now it's recording, so you can start.
Yes, we heard the message. So welcome again to our third session. I want to first introduce our keynote speaker to you. It's Volker Markl. He is a German professor of computer science. He leads the chair of database systems and information management at Technical University of Berlin and the Intelligent Analytics for Massive Data Research Department at DFKI. In addition, he is director of the Berlin Institute for the Foundations of Learning and Data, BiFold. He is a database systems researcher conducting research at the intersection of distributed systems, scalable data processing, and machine learning. Volker led the Stratosphere project, which resulted in the creation of Apache Flink, which you all may already know. Volker has received numerous honors and prestigious awards, including 2 ICM Sigmod Research Highlight Awards and Best Paper Awards at ICM Sigmod, VLDB, ICDE, and EDBT. He was recognized as SAM Fellow for his contributions to query optimization, scalable data processing, and data programmability. He is a member of the Berlin-Brandenburg Academy of Science. In 2014, he was elected one of Germany's leading digital minds by the German Informatics Society. He also is a member of the Berlin-Brandenburg Academy of Science and serves as advisor to academic institutions, governmental organizations, and technology companies. Volker holds 18 patents and has been co-founder and mentor to several startups. And his talk will be, after Apache Flink, about the next big thing. It's NebulaStream data management for the Internet of Things, and we are very excited to listen to your talk, Volker.
So thank you very much, Sven. And so just to double check again, so you can all hear me well, correct?
Yes.
Okay, perfect. Yes, it's a pleasure to be here today, and thanks for the invitation. And I will talk about a new, or well, fairly new project, I should say, that we have been conducting with my team, that is NebulaStream, where our goal is to create a new system that allows for data management at massive scale, like in the Internet of Things scenario, which would be a typical setup for that. So what I should say, though, before I get started with the presentation, that this is not really my work in a sense. I, of course, have been working on the vision and coming up with that, but there is a whole set of people that has been involved in, creating and building such a big system, and that includes several postdoctoral and senior researchers, as well as research associates that are PhD students and also master students. And what I should say is really the credit for all the great work and successes to them, and it's really their work. With that, I will start my presentation, and I've structured it in 3 parts. So the first part is I'll try to motivate by talking about distributed data stream processing in massive heterogeneous environments. What are the game changers? What are the challenges? Then I will talk about specifically this new system, NebulaStreams, that we have been building and are still building. And I will also, at the end, give an overview of the current status of the system and conclude. With respect to data processing environments, we have been seeing an evolution. So if we look at data processing from the traditional viewpoint, then you can see it in this figure. And that shows that we have various data sources here, and we ingest data into a, if you wish, centralized system that might be on-premise and cloud, like a data warehouse or a data lake. And there is some applications and users that will issue workloads against the centralized system, and results will come back. So this is kind of the traditional scenario. And this scenario has been challenged over the last years in a couple of ways. So the first observation is that we have nowadays more diverse and rich applications and workloads. So we have, in addition to traditional relational algebra, so SQL-like applications, we have applications that require linear algebra, like machine learning, like in TensorFlow, or combining relational and algebra and linear algebra, like in, when you use pandas in conjunction with other things in Python, or like PyTorch as libraries. So a variety of different workloads that have to be served, and it's not just relational anymore. In some cases, this might just be applying more complex user-defined functions, in particular if we apply a machine learning model, but if we train models, so it could be something more quite involved. At the same time, we see that we have more heterogeneity in the compute resources. So it's not a homogeneous cloud-like environment anymore, but we have where you have now the distinction between big nodes and small nodes, like in an EC2 cluster, right? So there is, on the one hand, even a cloud environment, you already have, different like GPUs or CPUs in the systems. And there's a trend to more specialization in the hardware that is due to, as we all know, Moore's law, that is not holding in that way anymore. So it requires the manufacturers of processing units to specialize and diversify. So there's new chips, like of course there's programmable FPGAs, but we also see we have seen of course the development of TPUs or special streaming chips or special co-processors for encryption, like Intel's trusted execution environment. And we have to take advantage of those kind of resources in an efficient way in those new systems. At the same time, one thing that's changing is, so the data sources, on the one hand, they are, not just, pushing the data into the centralized system anymore, but we actually have more control over the data sources because we have sensors, and we can actually, the sensors continuously produce data. So we're not talking about batches necessarily anymore, but about streams. And the data, we have a bit more control in the sense that we can instrument the sensors when we want to receive data, so just to make sure that we do not get flooded with irrelevant data. And at the same time, the topology is not that flat anymore. The world is not flat anymore, but it's really, in some cases, a hierarchical topology that is really leading to a fork kind of environment where we have several nodes that combine the results and move it on until they bring it to some large computational device. And at the same time, this data, it's distributed, but it's distributed often also geographically in even some wide ways. And this means, of course, different types of latencies, and also has consequences with respect to availability of data sources and so on. So those are different aspects. And at the same time, some of those sources and even some of the compute nodes might be moving, and that means they may change with respect to network connectivity. They may require, have different latency characteristics over time, and may also at sometimes, not be available and come back available again, right? So those are all things that a novel system will have to consider. So if we sum this up, we can say that data processing reaches a new level of scale, distribution, and also heterogeneity. And in the following, I will describe and highlight some of the challenges and also, if you wish, opportunities with respect to new systems design. And the first aspect is the adaptive handling of sensor data streams, because if we assume that we have a huge number of sensors, and this is a key difference also between, traditional data processing platforms that have maybe 5 or 10 data sources. But if we look at IoT applications or those huge amounts of sensors, we may have millions of sensors, right? And we cannot continuously stream data from all those sensors. So we need to have some adaptive sensor handling, which allows to scale those large number of nodes without, avoiding over consumption of resources and suboptimal utilization. And one aspect here is that the state of the art in this context is really assuming homogeneous hardware and focuses on disseminating single queries, but does not really exploit the sensor capabilities. And some of those capabilities would be really adaptive sampling. You see this in this chart here on the right, where you see if we have a data stream that's here on the left that monitors some price over time, and there's a certain spike on the top, and then it drops, and then it moves on again. If we would do something like fixed rate sampling, which is what, if we do not know anything about the data, one would normally do, in particular if you just do not use the sensor itself, but just pull data continuously from the sensor, then we would have, in this example here, 15 values that do not capture the maximum and the minimum of this distribution and the overall outliers and spikes of this distribution well. So this means that adaptive sampling that you can see with less values achieves a much better result. And this requires us, however, to treat sensor nodes as first-class components and keep the dynamicity of the data in check. And this enables, of course, much more precise sampling and with respect to IoT applications. So this is one opportunity, but also, if you wish, a requirement for those novel systems. Another one is massive scalability, because if we look at systems at those types of scale that we are targeting, we need to support thousands of queries on millions of heterogeneous and distributed data streams. And there we really reach limitations on classic cloud-based systems and that cannot really receive the data from the IoT devices because there's just too much data. The fog-based devices do have limited computational resources, so they cannot handle that as well. And of course, one can only have minimal functionality for data analytics on the sensors. So that means we have to bring all of those layers together in order to efficiently process the data. And we need a system to orchestrate all of those different layers. Another aspect, and I talked about that already before, is the support for heterogeneous devices, in the sense that IoT environments consist of a wide range of processing devices. Some may be very small band or low power or low computational capacity devices, and others may be even, large compute clusters that are available in this environment and this topology. And in the state of the art, the systems often are hardware oblivious or are really built for one specific hardware, but no system really exploits the heterogeneous devices efficiently. And IoT environments here introduce new challenges like device diversity and limited energy budget. And the goal is, again, to take advantage of that in order to arrive at an optimal processing from data source to sink. At the same time, we need delivery guarantees. We are operating in a distributed system, in a heterogeneous, massively distributed system. And the interesting observation is that depending on the application, there may be different types of consistencies that are necessary. It may not always be that one needs exactly once delivery. And the interesting observation is one in such a system would want to trade off consistency, availability, and resource consumption in a similar way as how we in a relational database system set isolation levels for transactions, right? So for instance, there might be temperature monitoring applications where it's sufficient to have at most one semantics. Then there might be some accident detection where you want to have at least one semantics, but there might be some smart purchases where you really need exactly one semantics, and you should be able to set that depending on your specific application, and the system should be able to handle those different types of guarantees. Also, there is, of course, requirements on security and privacy, because if we talk about critical infrastructures that those IoT devices may be embedded in, we need to make sure that they are not vulnerable to being attacked. And this really means we have to process confidential data correctly and have to provide, encryption and also ways for the system to not be able to compromise that easily. And another technical requirement is transactional stream processing, because if we talk about data streams, very often we deal with discretization of data streams through windows, right? So we have to make clear that if we talk about stream processing, we deal with unbounded, continuous, high velocity data, and we need to discretize this data in order to operate on it. And discretization, in many cases, means we create a window over the data, and there's many different types of windows, right? Like tumbling windows or sliding windows, and they have different window measures like time-based windows or count-based windows, or there may be session windows that are defined in different ways that are triggered in a certain way. Triggered means that we apply a function on the content of the window. And there's also different types of window functions like aggregation functions. And what all of those windows though have in common is they are state, right? So in order to maintain a window, we have state. And this is a bit different to many other operations, like in the relational algebra setup, where we are purely functional. We are moving data on from one operator to another operator. But here we have to deal with state, and state has to be consistent, it has to be transactional, And we need to make sure that we read and write with certain consistency guarantees. And we have to have those shared mutable states because we have that in a distributed setup in order to implement windows, but also for implementing some kind of other functionality, it may be necessary to have this kind of state. And that's why we have to make sure that we deal with transactions in the stream processing. Then those items that I have described so far are, if you wish, some more technical core requirements for the system, for the engine. And there are some other requirements that are, if you wish, on a different level. It's more about the application, about application programming interfaces, about the use. And an observation here is that one does not need, if we talk about IoT or if we talk about in general stream processing based on sensors, we do not only operate with relational data that filters and joins and aggregates data. I already mentioned there's some others like linear algebra, but there's also digital signal processing, which is required, or in a weaker sense, also time series analysis that is required because often one has signal logic that is, to interpolate for missing sensor values, to apply noise reduction filters, or do fast Fourier transformation for spectral analysis. So all of those should be part of such a system. And the observation is that there's not really a good amount of support in distributed stream processing engines for digital signal processing. And in particular, it's also clear that memory and compute intensive DSP operators are unsuitable for low-end fog devices. And also there are some operators there that are not commutative, so which makes it harder to optimize them because they require event ordering, and one has to take provisions for that. But one key thing therefore is to integrate tightly those signal processing operators in the execution engine, because this would enable a new set of IoT applications. Examples would be like gunshot detection from audio signals in the city, right? So this is one application requirement. Another application requirement could be efficient spatial analytics, because a lot of the phenomena in the IoT are location dependent. And that means that a lot of IoT applications may require some form of spatial processing. So spatial queries that, determine proximity, find points in regions, spatial joins, or the usual spatial operations. And there are some, cloud tailor solutions, but they have offer an inefficient use of resources. And at the same time, if we look at environments like transportation or public safety or even healthcare with wearable health trackers, there's a lot of potential for spatial analytics. Another example is complex event processing. Complex event processing really means we try to detect patterns of events as they occur in sequence and then automate decision making. And usually that's done by having some form of a finite state machine or some other kind of a state machine that recognizes a series of events and based on that triggers some actions. And usually those CEP engines rely on a central system, but of course at the scale we are targeting, that's hard to do. And for that reason, we are looking at, and we believe that in the context of such a new system, one needs to have complex event processing as a core component. And of course, last but not least, there is machine learning. And machine learning is this complex workflow, or general data science workflow of data gathering, cleansing and transformation, training, evaluation, materialization, and deployment of a machine learning pipeline. And those complex machine learning tasks would really benefit from being deployed on IoT devices, in particular, if we can, in this context, have some form of federated learning that distributes the processing by having local and distributed models that allow for lower latency and reduced network load and latency during the inference. And current systems really separate this or combine, frameworks like PyTorch, scikit-learn with, traditional batch and stream systems like Flink or Spark. But it's not really a good amount of support yet here for inference in IoT environments. And this would be another requirement. So with that, I have talked about, on a high level on what are the challenges and opportunities, what's the game changers if we look at the big picture of distributed data stream processing. In the second part of my presentation, I now want to talk about the contributions that my team at TU Berlin, DFKI, and BiFold has been making so far, and that we will continue to make, and we would hope to build a community around it and engage others in building a system that meets many of those requirements. And for that, we are trying to build this NebulaStream platform. And I will give you first an overview of NebulaStream, show you NebulaStream in action, and then we'll look a bit under the hood, talk about some technologies like query merging, operator placement, hardware stream processing, and then I will give you an outlook on some current issues that we have done research on already, we've published research already, and we are currently working on integrating this into NebulaStream. And with that, let's get started. So what is NebulaStream? So NebulaStream is an IoT data management system, and the goal is to have a general purpose end-to-end open source data management system for the IoT. And we strive for an out-of-the-box experience with rich data processing functionalities and a high ease of use. We have for that a variety of query languages that we try to support on top of a architecture that has the topology that I had outlined before. So the topology is geo-distributed, massively distributed, hierarchical, and it may have moving sensors or even compute nodes in this environment. And it is highly heterogeneous with respect to having GPUs and CPUs and data sources that we have control over, so that we can do this adaptive sampling from the sensors and so on, right? So we have this way of operating on processing data streams. And NebulaStream provides a couple of query languages. So we have here Java, C++, Python, SQL, and the patterns specification language, which is for complex event processing, so PSL. So those languages that allow us to interact with the data streams. And as APIs, we are looking to build. So we have already something for stream processing, which is essentially window operators, relational operators. We have some things already for complex event processing, and future work that we don't have yet is really in the area of spatial data processing and linear algebra. But all of that should be part of that system. And you can also see a key requirement of such a system, as I revisit that in a second again, is that we want to deal with different kind of languages here. So this system has to be polyglot to some degree. And the questions that we try to answer here and by building the system is, how can we support millions of devices, both sensors and also compute nodes? How do we exploit the hardware heterogeneity so that we can really take advantage of the different CPUs, GPUs, and the corresponding characteristics that they have? A key challenge then is also how to execute thousands of concurrent queries in such a system. And there, of course, I thought this can we, share some of the computations. How can we detect that? How can we do this efficiently at this scale that we are talking about? Also, how do we support heterogeneous workloads? Heterogeneous workloads here again means they may be polyglot with respect to having specifications in different languages and so on. And how do we handle failures without losing data, which deals with consistencies, which deals with state transfer in an efficient way. And of course, the system is dynamic. We talked about that before already. So there may be nodes coming in, nodes going away. There may be failures. There may be changes in the data distribution because of the long-running queries, which may render a particular execution strategy that has been deployed not optimal anymore. And at this moment, we need to adapt the execution based on the data characteristics that may have changed. And for that, of course, we need to monitor the data characteristics in the first place, so determine what's relevant to be monitored, and then make this available. And based on that, having some monitoring and traditional, we would call it a MAPE loop, right? Monitoring, analysis, prediction, and then execution loop that as a feedback loop allows for adjusting the execution. So this is NebulaStream, and now I will describe to you a bit an application scenario. So first we look at the high level, how do we use NebulaStream, and then we will look under the hood. And how do we use NebulaStream? So what we have built here is we have built in order to test NebulaStream in a variety of settings a simulator that we call NebulaCity, which is really a simulator of a smart city. And the simulator provides an architecture of a smart city. So you see in the smart city, you see like factories, you see energy producers like solar panels that are on some roofs, but also you see, if you look at the very right corner, lower corner, you see wind turbines that produce power. And you of course have cars that move around. You have hospitals that admit patients, and all of that is instrumented with sensors. So in particular, and this is an example that I will go into a bit more detail now, is an example where we have smart meters. So we have sensors that are smart meters that are in every energy consuming operations, so in the houses, in the factories, and so on. There is smart meters that tell us the energy consumption. And of course, the energy producers like the solar panels and the wind turbines also have information on how much energy they produce, and of course also where the energy is routed to which consumer. So I will use this as an example. And what I want to point out here, because of a bit of a concern over the quality over the network, I'm not going to show you a demo video that shows you the demo, but I have given you a link here. The first link is a link to the actual demo video that will show you first Nebula City, the simulator, and then it will show you the deployment of queries. It will show you essentially the screenshots that I'm showing you actually in a live demo setup. And the second one is the NebulaStream YouTube channel that we have, where you can see also further videos and presentations on NebulaStream. But I will now guide you through the demo through screenshots. And the first observation is that we have in this demo, we have first the NebulaStream Smart City, which is our simulator that continuously produces data streams, right? We have data streams on the one hand from the energy producers, we have data streams from the consumers, but there's also other data streams like from hospitals and so on. But for this example, we just focus on the energy part. And this data is ingested by NebulaStream and processed by NebulaStream, and there's some queries that will then enable some actuation. On the one hand, to really control the smart city based on the computations. And then there is also NebulaStream provides some data to a user interface so that we can actually use some, conduct some analytics on that and visualize it. And that's really the part that I will just show through some screenshots here. So the first thing is, so here you see another screenshot of Nebula City in the demo. So one can scroll around and look at the various sensors that are deployed in those different, buildings or cars or whatnot, and what they produce. So you can see that that's really the simulator. And the observation here is we have sensors for wind turbines, we have sensors for solar panels, and of course we have sensors for all the smart meters. And if we now would look at a sensor of a specific wind turbine, we see, for instance, this wind turbine, depending on the wind speed, it produces a certain amount of kilowatt per hour, right? And this information is continuously streamed into the system. And if we now have a particular query that we would like to ask, then we would say something like, do we really produce enough energy to satisfy all demands if we want to monitor that? This would be a query that, and I describe the query now, here's a sort of a data flow graph that would query all of the wind turbines. This is a union of all of the wind turbines is one stream. Then there's a stream of all the solar panels. And it would union those two so that we have all of our power sources. So those are the two power sources of Nebula City. And then we have a window where we build an aggregation. So the window actually is over a certain time, like over an hour or so. And for this hour, we will then compute the production. And then we join this with the consumer. So we know to the consumers to which each of the energy is routed, we'll conduct the join. And then we can send the data out for analysis, or we could also do some action based on that. So if we look how this query looks like, this here is one of the APIs of NebulaStream. This is now, if you wish, object-oriented, almost functional kind of API that's in a Java or almost C++ kind of setting that just uses some keywords. So like from the wind turbines that we union with from the solar panels, we build a window based on some attribute like the producer, where we sum up the produced information, and then we join this with the consumers based on the producer ID. and then we would create the output. So this is just an idea of this query. And if we look at NebulaStream, so this is the main landing page. If you go into the system, so you have an overview of the applications that are running in NebulaStream. So for query catalog, you have the topology of the cloud fog environment that NebulaStream is running on. You have a source catalog, and then we have some ways of visualizing the results. And of course, there's some settings that one can look at. And if we now look at the sources, so there's a couple of sources. So in this case, we have this consumers data stream, we have the union of all the solar panels data stream, and we have a wind turbines data stream. There's a couple more that are not so important here, but those three are the ones we are focusing on for this query. And like if we now inspect the solar panels stream that has this solar panel group ID, it has a consumer ID, produced power, and a timestamp, and similar for the other streams, right? And if we now look at the query catalog, we would see there's a query, and this is exactly that query that I talked about before, the query with the wind turbines, that's union with the solar panels and so on. So this is the actual query. And this is a query that would be running, as you see in this example here. There's also another query running. We could, of course, also inspect the other query, but those are the two queries currently running here in the system that we see. And we can also look at the query plan for this query. So you do not see a lot here, but this is really a representation of the query that shows operators as nodes and the data flow as edges, and the leaves of this tree would be data sources, and the root would be the data sink that is used to process the data. And this is showing you actual representation. And now the question is, of course, what happens? So this query has to be executed on a topology, right? So there is a topology that's maybe in NebulaStream, like if you would click on topology, you would see that that's a topology that consists of those 4 nodes that may have different capabilities. Some of them may be Raspberry Pi, some of them may be, you know, large clusters and so on. And those different nodes are part of the system, and the query will be deployed on that. And you can also look at the result visualization, and then you would see, for instance, the data stream over time, and you would see exactly the output of the query, which is the consumed power and the produced power over each point. It could be interesting then, because here you see there's some areas where we have a spike, where the consumed power goes up, the produced power goes down, and those could be areas of intervention, if you wish, right, for the power company. But this is just to give you an idea of the application scenario. And now let's look a little bit under the hood. What does NebulaStream really do? How does it process those kinds of queries? How does it operate? And what happens is NebulaStream, it consists of a typical distributed systems architecture. It's massively distributed, as said, but we still have coordinator nodes and worker nodes. And the coordinator node deals with a variety of components, like the query optimizer that will look at deploying the queries in an optimal way and maybe even redeploying them. There is the query and source catalog that maintains the queries that are currently running, and the sources that are available. And the important thing is we'll see that that's a big graph that has to be managed. And then there's a topology manager that, of course, manages the topology of the system. And there's an RPC system for communication. And this coordinator interacts with the worker nodes. Of course, it deploys queries there. It monitors the query status, and it also gathers statistics that would be used, for instance, for re-optimizing and in general monitoring the health of the system. And then each NES worker node has a query compiler, because we are compiling the query specifically on this worker, right? And you will see that in a second. We are not using a managed runtime with interpreted code, but we actually really compile it in order to be hardware efficient. So we have, for that reason, we have the compilers there. And we have to deal with operators. Some of them are stateful, like window operators. I talked about that before already. For that reason, we need to have state management component. And of course, there's sensor management that will be able to retrieve data from the sensors and do so in an adaptive fashion. And of course, in order to process those operators, each NES worker has a task based data flow engine, and those workers communicate because they will send intermediate data streams to each other in order to collaboratively produce the result of the overall running queries in the system. And I will show now how this works for a particular query with an example query. And I'm using a little bit of a more simplified version of the query that I just showed you, which is a query that just unions the wind turbines and the solar panels and builds the aggregate over a certain time. So it's essentially a query that has two data streams, which are, however, again, unions of a massive amount of other data sensors. And then it will perform a window computation. And so such a query, if we look at the query lifecycle, is processed in the following way. So the query first, we have this query that has, the two data sources, then it has the operator as the union, and then it has the window and the aggregation here on the top. This query is integrated into what we call the global query network or global query plan. That's all the running queries in the system. So this is essentially the state. And the first thing is to bring it into the system. And then once this query is in the system, this is a logical representation, this global query network, we need to actually deploy the query. And for that, we have this execution network, and the execution network maps the query network to the topology. So we have this IoT topology, and those two are being brought together with the corresponding questions about parallelization, replication, and other aspects. And that's really what the execution network does. And then it's deployed on the topology and being executed. And an important observation is that there is this cyclic arrows here, which denote that, of course, there's a continuous monitoring going on, and the system will potentially re-optimize. And it may re-optimize on a single node. That's a local decision, or it will re-optimize, and rearrange some aspects of the execution network based on some algebraic properties of the operators that are being deployed in this global query network. So if you have associative, commutative, or distributive operators, there's some opportunities for doing so, and that's based on characteristics that would show us what's better to optimize. So this is if we look at the overall query lifecycle. And now there's, of course, a couple of questions. And the first one is how do we really integrate a query into this query network? How do we come up with a shared query plan? How do we do this query merging? And so for that, I briefly zoom a little bit more into the query optimizer component that's running on a coordinator node. So essentially, first the query is parsed, and then the optimizer deals with that query. And the optimizer, if we expand that, it has first a phase of query rewrite that creates a standardized version of this query, so which would be better to optimize. So standardizing predicates, standardizing also the order of attributes, but also creating some other forms of standardization that we would know from traditional database systems based on the algebraic properties of the operators. And then, in order to do the merging, we do this based on signatures. That means we compute signatures from a query, and the signatures are based on, so the ones of you who know relational query optimization may know interesting properties. So those would be things like predicates, like projections, like interesting partitions, and so on, a traditional optimizer. And we use a similar concept here. And we use, for instance, windows, which you can think of like partitions. We use predicates, and we use also the projection attributes as the important parts of the signatures. And then we need to determine similarities among running and newly arriving queries. We need to identify that. And the way to do that is essentially you have to do some logical reasoning. Is the signature already contained? So it's really a query containment question, right? And there are several ways of how to deal with this query containment. And the one we chose is essentially performing theorem proving. So we're running a theorem prover that identifies the sharing. And if we have identified sharing, then we can update this global query network, and then the queries can be placed. So this is how the incremental spin query merging works, and it can be quite effective. So we have a paper that's currently under submission and evaluation, And you can see, of course, this now depends really heavily on the amount of sharing in a specific setup. And we had here, in this case, it's an artificial workload, but just to test how effective sharing can be if there's a certain amount of sub queries that are being shared. And it can be really orders of magnitude improvements in throughput that you can achieve here quickly if you have the right amount of sharing, of course. The second question, if we look at this query lifecycle, is now operator placement. So this is really the question: if we have this global query network and we have a topology, where do we place a particular operator in this execution network? So where should this SN1 or this O1, why should it be worker node 1, right, when it gets deployed? So this is the second question. And this operator placement, the way we do it in NebulaStream, so this is currently still an area of research to find what's the best way of doing this. But we have a couple of strategies that we have implemented and trading off. So we have strategies that are really constructive placement, like bottom up, starting at the leaves to place the operators until we reach capacity based on some metric like transfer bandwidth or the actual operator or node capacity or other aspects, right? So we reach some threshold, and in this way we place them bottom up, or we can do the same top down. And then there's also cost-based placement by using some cost models that, however, it's also a question now, what would be good cost models that are interoperable in this heterogeneous environment? And for that reason, we have not yet a completely conclusive answer, but we offer a variety of strategies right now. And then cost-based placement, we have 3 strategies like random search, integer linear programming, and a genetic algorithm that we use. And we're currently working on determining, hopefully, a way that we can do this automatically and don't have to, have a user instrument what kind of placement strategy should be used, right? So right now, one can actually select some placement strategies as their default strategies, but this is an area of research. Then another question is now, if we have deployed the operators and now we have a particular worker node that is running an operator, how can we efficiently leverage this node? And this is really where we see one key difference between IoT applications and NebulaStream and other data processing systems like Flink or Spark or many of the others, because our goal here is to really leverage those individual nodes efficiently, and in this way achieve much higher throughput and performance, and in this way save energy and be more efficient. And before I get into that, though, we have conducted a study, and we had a paper here at VLDB 2019 on that, where we analyzed stream processing and we showed the inefficiencies of the existing systems, because the current stream processing engines use hardware resources inefficiently. And one reason for that is that they use an interpretation-based model that is really based on managed runtimes, and you interpret the queries using this traditional open next close model of processing, right? And if we have this model, then this interpretation causes pure cache utilization, both from the instruction cache and the data cache perspective. And the second point is that the upfront partitioning causes a high overhead on single node deployments. So like the systems perform upfront partitioning, and on single node deployments, this really causes a very high overhead. At the same time, the SPEs do not really react to changing data characteristics, and that's important because over time, the data characteristics may change if we have long-running queries, and that means if we had done some optimizations, like for instance, we did speculative execution on a selection, right? There's an if statement, and we execute the site based on a certain selectivity assumption. Then that was true for some time, and then suddenly it changed. It's not true anymore, and the other side should be speculatively executed. Then we should change that, and the systems cannot do that. And there's other ways of, reacting to data characteristics. So for instance, we could exploit value ranges for hashing through static memory buffers, or we could, exploit value distributions to decide among global versus local hash maps, because global hash maps work better if we have a rather uniform distribution, and local hash maps work well if we are skewed, right? So those kinds of trade-offs, and this, however, is dependent on the data characteristics that may change. And for that reason, the system needs to take advantage of that. And Nebula streams should, for that reason, be data and hardware conscious. And we actually, for that reason, have, based on other work that we have done, and you can read the details on that in our Sigma 2020 paper, Grizzly, we have proposed a adaptive query compilation technique for efficient stream processing, where the observation is that we have a streaming query like this example here, that is a data stream that's filtered and then has a window aggregation. So if we have such a data stream, then we want to compile this instead of having an interpretation-based approach. And we do so by following the produce consumer model, using this compilation-based approach that has been introduced by Thomas Neumann for relational data at rest. And what we do in this approach, actually, we take the query and we segment it into pipelines. And this segmentation takes place. So in this example, we have the filter, the window assignment, the aggregation, and the window triggering as one pipeline. After that, we have a dam, a pipeline breaker, and the filter that is carried out on the window is in its second pipeline. And then for each of those pipelines, we can do fusion of operators, so we can combine them, we can optimize them, improving cache utilization and so on, and then generate code, generate efficient code. So what we do is we generate code variants with different cache characteristics, right? So using, as I said before, examples, right? Depending on some assumptions, right? You might use different types of local versus global hash maps, predication in order to have speculative execution based on predicates and so on. And there's different code variants, right? And one of those code variants is chosen for execution. And then the system is adaptive in the sense that it will monitor. So it's data conscious. It will monitor if the assumptions for this code variant are still true. And if not, it can do in this case, local reoptimization just within its runtime and use a different code variant in order to improve performance when needed. So this is Grizzly, and in NebulaStream we actually have adapted Grizzly, and so we have in NebulaStream a bigger picture, which is we have the central optimizer that is looking at the big picture globally in the distributed system, and then for each worker we have this local optimizer that's based on Grizzly that arrives at this pipeline execution plan after the query segmentation that is given to the query compiler that generates the code and goes to the adaptive execution engine. And we have a task-based execution engine. And the reason for that is we need to be efficiently data parallel, and we need to have some in order to simplify parallelization and be efficient here, right? So we need to have some lock-free execution. Ideally, leveraging a ring buffer and atomics, right? So that makes things much more efficient. And this is what we have in our task-based execution engine. And of course, there's this profiler that will re-optimize when needed. It will re-optimize locally, and in some cases, it will have to re-optimize globally, which is then looking at this global query network. And the single node performance, you can see there's a really strong improvement over the state of the art. And this is also highlighted in this paper, in the Grizzly paper. So there we have seen, the Grizzly achieves a really high throughput over other research prototypes. But what we can see is now, if we look at NebulaStream and the end-to-end system, so this is on the Yahoo streaming benchmarks on an 8-core server, we can see, and I want to point out that this is a log scale, right? Flink, for instance, is a state-of-the-art strong system, achieves 16.3 million records per second. But in NebulaStream, we almost achieve 400 million records per second. And other systems like Spark or Kafka are way behind, right? So the other thing that's interesting and important here is we are taking advantage of heterogeneous hardware. So the single node performance on different hardware devices, like small embedded devices like Raspberry Pi, like Jetson AGX, or the Apple M1, but also if we go to the high-end machines like Xeon Silver or the Xeon Platinum, you see a corresponding good performance across the entire spectrum, as it would be expected if you do hardware-targeted code generation as we do. I want to give, to the lack of time, a very quick outlook on two other features, and then I will give you references where you can read this up. So one is, and I mentioned that before, is supporting polyglot queries, which is queries that combine relational operators with user-defined functions that are written in different languages. Like here I have an example where a SQL query calls in this case, and a SQL query that in this case, for example, would be a bike sharing company that would compute a trip profit based on some distance. So it has a definition of a trip profit function that is written in JavaScript. And it also has a distance function, the haversine distance, or distance on a sphere, that's coming from a Python library. And it's also interesting to point out that even the JavaScript itself would call this distance function. And the question is now, how can we efficiently deal with queries that have those different languages in their specification? So here we have, as I said, we have relational operations like the from, like the selection, but that calls out to both JavaScript and to Python, and the aggregation here calls out to JavaScript. And the bottlenecks of those kind of polyglot workloads are that we have to invocate those queries at runtime, right? So we have to invocate a language runtime. There has to be data exchange and also potentially data conversion, because it may be a different data representation between those different languages. And what we are looking at is a tight integration between the compiled pipelines and the UDFs to efficiently support those polyglot workloads. And we actually have done some work on that we have published in RealDB 2021 already. And there's a system called Babelfish that combines relational operators with Java, Python, and JavaScript UDFs. And it does so by introducing a holistic intermediate representation for polyglot queries. And we are leveraging the truffle and Graal technologies, so essentially the single static assignment forms, in order to enable holistic optimization and execution across operator boundaries. And in this way, we eliminate the boundary between relational operators and UDFs and achieve much higher efficiency. So this is one part. And the other part that I wanted to briefly mention is managing large state. So, and I will, for the sake of time, not really go into details here, but just point out. So we have also done some work on supporting terabyte-sized state with on-the-fly fine-grained reconfiguration of running queries, which is key. So existing systems, so if you look at Flink or Megaphone, they get into trouble here. So the reconfiguration time is quite high. And we have proposed a system called Rhino that has two protocols, a handover protocol for reconfiguration that is essentially allowing us to efficiently move data over, and a state migration protocol that is proactive in some way, that removes the state migration bottleneck. And if we see that, then we really can move terabyte-sized state very quickly and achieve really 3 orders of magnitude latency reduction. And this is also a paper. You can read up the details. It's a Sigma 2020 paper. It's published, and you can look at that. And we're looking to integrate all those into NebulaStream right now. So with that, I want to give you the current status of NebulaStream and conclude. And the first statement here is, so NebulaStream, we are actually seeing an active and growing community. So currently we have more than 30 contributors to the system that consists of 250,000 lines of code right now, with clients for Java, Python, and C++. And we are using it already in a couple of research collaborations with the University of Manchester, some universities in Italy, CNET, and TU Graz, and also a collaboration with Siemens. And two projects that are worthwhile mentioning are the Extra project, where we used NebulaStream as a data acquisition platform in conjunction with Apache System DS from TU Graz, Matthias Blüm's group, and Siemens, where we looked at determining the quality of paper in a paper mill doing paper production. So NebulaStream is the data acquisition engine in paper mill in this example. And there's another project called Elegant, where we are looking at secure and seamless edge to cloud analytics where NebulaStream is providing the runtime for this analytics engine. And I should point out that NebulaStream is, so since we've built Flink, right? So if I look back at that, we are at a level where we are ready to do the first engagements with, which I would call bleeding edge customers, which is people that really have a good understanding of the system and are ready to work with the system, but also are willing to help us to advance the system and you know, improve the system based on some missing functionality in particular. But we have, you know, already a reasonable documentation that's out there, and here you see a link to the documentation that describes NebulaStream, the features and concepts, but also has a demo and a tutorial to tell how to use it. It describes the APIs, both the stream processing and the CEP API that I briefly mentioned before with their data types and expressions, as well as the clients, and also the development IDEs if one wants to really join the open source. And this leads me to my almost last slide, which is a call to action. So please, you know, help us to try and contribute NebulaStream so you can try it. If you go to the NebulaStream website, the link is down there. You can actually see a tutorial, and you can also get the code base. And at this moment, because the code is not so ready for general use yet, we have not made it freely downloadable yet. But if you request access, because we want to make sure that we can support people who work on it, right? So, but if you request access, then we can give access to the code base. And with that, I would, you know, say, be part of the journey. So there is lots of things that can be done also from a research perspective. So there's still a lot of questions in geo-distribution, graph processing, privacy, risk, continuous operation, learned structures like indexes or materializations, security, persistence, federated learning, accelerators at the edge, placement, and also 5G or 6G. What do they mean in this context, right? There's lots of room for research, and NebulaStream is a great playground. And so to summarize, NebulaStream is a general purpose end-to-end open source data management system for the IoT. We would be happy if you join and collaborate with us, either directly in your institution, or if you are graduating or looking for something new. We are also hiring, so we have opportunities. So we have some tenure-track postdoc positions that are becoming available now soon. And we also have fully funded PhD students positions available if you're interested in building systems technology. And with that, I thank you very much, and we'll be happy to answer questions.
Yeah, thank you, Volker, for your wonderful and excellent talk. I think we should start or stop recording right now, such that we lower the barrier for asking questions. Simon,